Welcome to the course EE672A, Analysis of Modern Wireless Networks. My name is Abhishek Gupta, and I will be your instructor for this course. This course will have 2 lectures each week, approximately of 3 hours. They will be pre-recorded and released either on MOOCit or YouTube. In today's session, we will talk about the course schedule and its content, and we will also have a short introduction to stochastic geometry and the analysis of wireless networks. The course will cover tools from stochastic geometry. So what is stochastic geometry? Is a study of random geometry. In wireless network, as you will see, sometimes the device nodes can be modeled as a random pattern. So the stochastic geometry tools can be used to analyze them. It will be used to model and analyze modern wireless systems that are being used in 4G, 5G, and even beyond 5G systems. We'll also look at some examples for that. So objective of the course is like that. After completion of the course, you should be able to apply these tools in your own research. So this course is not only about learning them, but you should be able to apply them in your own research. You will see that stochastic geometry is rather a new tool. So there are still lots of open research problems with that. So I hope that once you have done this course, you should be able to even take some research problems and this course should be useful. The course also has some project content that will help you getting started on these research problems. The prerequisites of the courses are that you need to know basic probability, you need to understand what is random variable, random processes, and you need to have a working knowledge of calculus. Since the course is about analysis of wireless systems, let us first see what are wireless networks. So wireless networks, we know it's a bunch of different nodes talking to each other wirelessly. Wirelessly means the communication is happening via electromagnetic waves. And there can be multiple transmitter receiver pairs which are already present in the system. And you may own one of them or you may own all of them. So that's a different thing. And how this communication is happening, that depends on what kind of technology or standards you are using. You may have heard of Wi-Fi, LTE, cellular, millimeter wave, all those technologies. And they are just different protocols on which how you implement this communication. But on the background, they are all wireless communications. And they have a basic fundamental framework to study their performance. So suppose there is a receiver and a transmitter, and then this transmitter is transmitting some signal to this receiver. So what is the most important thing you will want to understand to see how this performance is? So we all know that transmitter is transmitting with some transmit power, and the receiver is receiving with some power. And based on the channel in between, the distance between, this transmitter power will reduce, and the receiver will receive some reduced version of reduced strength of the signal. And this signal strength, if you talk about its power, we call it received power. That basically tells you how reliable is the communication. If the distance is small, you will have and the transmit power is significant, you will see a very strong signal, and you will be able to receive the communication easily. But if this signal strength is less, and mainly compared to the noise, hardware noise, you will not see any communication. So what we say here is a desired signal power, because this is my desired transmitter. I want to receive signals from it. So whatever signal strength I'm getting at this receiver from this desired transmitter, we call it desired signal power. And let's denote it by PR0. And then if you have multiple transmitters, right? This is your desired transmitter, this is you, and there are 2 other transmitters. So what kind of situation is this? Suppose you are living in an apartment, you bought your Wi-Fi router, and you want to connect, you want to watch a video on your phone, and this wireless router is transmitting to your phone. But then there are other apartments nearby, and your neighbor may be using this Wi-Fi also, and they all use the same frequency. So their Wi-Fi routers may also unknowingly translating to you.
Okay, so they are actually transmitting their own device, but you cannot put boundary on the electromagnetic wave. They can go anywhere. So even if it's communicating to their own transmitter, the signal strength will also comes to your phone. And if the strength is high, those will cause interference to your desired link. Okay, sometime you may have seen that you check your phone and the signal strength is good from your router, and still you're not able to receive any signal, and that may be because the other transmitters are also uh, giving the phone a good strength of signal. So in that case, all this receive power will be added up, which we call interference power. And then because we cannot decode this interference power, this will also contribute to as a noise in the as a noise, right? So when we compare this signal power, we want to compare it with noise plus interference. And if this signal power is significantly enough, uh, more than noise plus interference, then this communication can happen. Okay, so this ratio is denoted as SINR, which is signal to interference plus noise ratio. And we just take noise and add interference and then divide it. So if this SINR is more, suppose 10 times or 100 times, you will see get a very good communication. And if this signal strength is low, which means either noise or interference is high, then you may not see any. You may not be able to decode the desired thing. So why SINR is important? First of all, of course, the communication reliability depends on SINR. And then again, if I ask you, what is the key performance of any network in your perspective? Right? When you go to an operator, cellular operator, and buy their SIM, what is the question you ask to know which operator SIM is better? Right? And we talk about data rates. Right? A company claims that I can give you 100 Mbps, I can give you 10 Mbps, so you will of course buy the 100 Mbps. So eventually this data rate is very important. The data rate is nothing but how many bits you can transmit or you can communicate per second. Even these technologies or standards mainly depends on this data rates, like 3G is 10 Mbps, 4G is 100 Mbps, 5G claims to give you more speed. And there are other factors also. For example, there is latency, how slow is the communication, how reliable is the communication. But in background, the most important factor is still we talk about the data rate. And there is a famous equation which tells you what is the maximum data rate you can achieve from a link based on its SINR. And that is given by Shannon. And this says that the upper bound of the rate is equal to available bandwidth W into log 1 plus SINR. And available bandwidth is limited. There is a bandwidth scarcity, and of course, the operator has to buy those spectrum, which is costly. So it's a costly investment. So you cannot increase it beyond a limit. So only thing you can control here is SINR. If you give very good SINR, you will get better data rates. So when you talk about this performance, we generally talk about what is the SINR you are getting, and from that you can guess the data rate. So that was true for all communication links, but in this course, we want to focus on wireless links. Okay, and what is the difference between wired and wireless? In wired, you have a dedicated line between transmitter and receiver. There is no interference going on. Even if you have multiple transmitter receiver pair, you can orthogonally schedule them so that they don't interfere to each other. And that is not the case with wireless communication, because every device is sharing the same media. If some other nearby device is also transmitting, it will interfere with you. And there is another more level of attenuation is also in wireless communication. In wired links, due to dedicated guides, you will have very small propagation losses, and your communication can happen with over a wide length. But of course, you have to invest on creating and constructing these guided lines. In wireless communication, there is not such requirement for creating these guided links, but the problem is because of this is a wireless communication, a wireless propagation, there are there's a high level of attenuation associated with it. So we have to understand what kind of propagation it is, and we are not going to completely talk about in detail because this is a topic of a new course, but we'll just take it a short discussion on it. So main challenges in the wireless communication are fading, multipath, and shadowing. Okay, so what is multipath? So if you have a transmitter and receiver, and you may either receive the same signal copy, or this signal can go to other directions and reflect and come back to you. So you will receive multiple copies of the same signal, and depending on the length and the properties of this reflectors, you may see some phase delays, some time delays in these signals. So the goal is how you can combine all these multipaths and get the best signal out of it. Second thing is fading. What happens if you have multiple parts and all these parts have different small components which can, these are called scatters, and when the signal passes through it, it can create random delays and a random attenuation. So as a combination effect, you will see a signal which is the attenuated and phase shifted version of the original signal. And based on this location of these scatters and reflectors and the relative position of this transmitter receiver, sometimes you may get a constructive interference from multipath, sometimes you get destructive interference. So these fadings can sometimes give you a good signal strength and sometimes can give you a very low signal. So this fading is random and it changes very fast over the time. And the third thing is shadowing, which is more long term, which means if you have a tree or a big building in between transmitter receiver, the signal will always be blocked. So you have to either find another path where you can transmit or another transmitter to establish links. And sometimes these blockages can be really significant, such that no communication can occur. So how do we compute the performance of a network? So first we'll compute the receive power for each link. So suppose there is a transmitter and a receiver. So the total receive power at the receiver is given by this transmit power multiplied by a attenuation which is caused by the path loss. And it is generally modeled at some constant multiplied by a distance to power minus alpha. Alpha and C are path loss coefficients. Alpha is known as the path loss exponent and C is known as the near field gain. So if we just multiply P with Ci minus alpha, this will give you the attenuated power. Then there are other factors, for example, the fading and the shadowing, which will further attenuate the signal. These are modeled by random variables. Let's denote fading by H random variable and shadowing by G. So there are some distribution to it, and those distributions are based on experimental validation, and they depends on the environment and the scenario of the network. So for this link, the receive power at the receiver would be equal to fading into shadowing into transmit power into Ci minus alpha. So you can see that with distance, this receive power decreases. So that is the geometry component of it, that depending on the geometry, depending on the locations of these transmitter receiver, the receive power may change. So desired signal power, in this case, from the transmitter would be PR0 would be H0, G0, P0, C1 minus R0 alpha. So here I am denoting everything at 0 just to denote it. They are the parameters corresponding to the desired transmitter. Similarly, if there are multiple transmitters, each of those interfering links will have a similar transmit power. Of course, their distance would be different and the fading would be different. And many times it is assumed that different links have independent random variables to denote their fading and shadowing. So if there is ith base station, ith transmitter, the receive power at the same receiver would be Hi, Gi, Pi, C into 1 upon Ri alpha. And if they are multiple, I'll sum them all. So a signer will be given as this signal power divided by this interference plus some noise, which is the noise depends on the bandwidth and the hardware impurities. So once I know this assigner, we can figure out that this assigner is random because there are many random variables in the expressions. Moreover, if the user location is also random and the transmitters are also random, then the distances are also random. So this assigner itself is a random variable, and to characterize a random variable, we cannot give one number. To characterize a random variable, we cannot just give one number, but we have to give a distribution. So if we write the distribution of assigner, that is known as the probability coverage. So probability coverage is nothing but the complementary CDF of assigner. For every any threshold t, it is the probability that assigner is more than threshold t. So what can be this threshold? Sometimes we say that if we want a audio communication, then the assigner should be more than 0 dB. Or if we have a video communication, then the assigner should be more than 15 dB. So in that case, if I calculate the probability the assigner is more than 15 dB, that probability will give us that what is the chance that if I do a communication on video, the communication will be successful. Same as assigner, I can also compute rate, and give rate is also a random variable, so I can talk about the distribution of rate, which is known as rate coverage. So rate coverage is nothing but the probability that a rate would be more than some threshold rho. Other parameters are given as area spectral efficiency, which is number of bits transmitted per unit area, which is given by rate into transmission density. We'll talk about more about this performance computation later. But you will see that most cases start with computing the assigner. So what are the examples of these wireless networks? First is ad hoc networks. Ad hoc networks are pairs of transmitter receivers, and they are predefined. So ad hoc networks are a combination of transmitter receivers pairs, and they are predefined pairs. It means this receiver only wants to talk to that transmitter. So an example would be like your Wi-Fi routers at different homes. So if there is a colony and every house has a Wi-Fi router, so and mobile receiver. So this mobile receiver only want to talk to their own Wi-Fi routers. Even if there is another Wi-Fi router of your neighbor which is closer than you cannot connect to it. So the set of these predefined pairs of transmitter receiver are generally known as ad hoc networks. And this ad hoc is coming because they are randomly transmitting and idling independent of the other transmitter receiver pairs. So suddenly they start transmitting, they transmit for some time, and then they can become idle. So at a particular point of time, some of these transmitters can be active. Then they are randomly located in sense that there is not fixed deployment. Everyone can deploy them differently at their house. So we talk about here not exactly what is the cell-to-cell distance, but the density of pairs. What is the density? How many transmitters per kilometer square you can expect? So when we talk about a typical pair, we take one typical pair arbitrarily. We talk about interference from all transmitted device. And then for performance, we either can do a simulation. It means every time we generate this transmitter location, compute their channel, and then we compute the performance of the typical pair. These are industry standards. Like in industry, generally people do by simulation, and they take very complicated more realistic models. And I will also talk about some conventional approach to do it. But the question is, can there be analytical approaches which can give us some expressions which can tell us what is the impact of different system parameters? Similarly, the other network is known as cellular network. And in this network, there is a single operator which deploy many base stations over an area. And then if you are a user, you fall in one of the cell tower range. Okay, so depending, you can see there are different base station towers, and depending on the distance, they are serving power. the area is divided into small cells. Like this base station will serve this area because it has all the location for which this tower is the closest or in a better position. So what happens? The complete area would be divided into cells, uh, and each cell will be known as the coverage area of this tower. That is, we are calling it a cellular network because this is made from different cells. And this is more like a plant deployment. The operator makes a survey. Of course, the, this plant has some random component because you cannot deploy a base station anywhere. There are many political and geographical constraints. Then the users belongs to one cell only, and when it wants to communicate to any other user, it first connect to the tower, and the tower is connected via a backhaul link, a wired link to other towers, and then from that tower it talks to the other user. And this cell to user association can depend on the distance or other factors also. And again, when we talk about the performance, mainly we will talk about simulation, and there are not very analytical approaches available in the past to compute the expression for any coverage. Then the other networks which would be interested in the same cellular network, they we have downlink and uplink. So what does downlink means? It means there are different towers and the user want to download something from this base station. This is known as the downlink. So in that case, their base station are the interfering links, and this is the tower in the cell you are, that is the desired base station, serving link or associated cell. And the uplink, it's opposite way. The user communicate to the base station tower, and the other users in our different cells are also communicating. So interference occurs at the base station from different users. Then an extension is known as the heterogeneous networks, which is made from multiple different types of base station. So you can see that in a typical cell, you can have a base station tower, which is serving the complete area. Then there may be some relays in between, which will serve a smaller area, especially those areas which are deprived of coverage because of some big blockages. Then some people on their own buildings can deploy femto and picocells to serve a particular area. Like in a downtown, where there are many shops, they can establish their own small tower, their small cell, which will serve this. And now these different types of base station differ in their transmission techniques, in their power, in their spectrum uses, and their deployment can also be different. So this is known as the heterogeneous network. And then in the 5G, we have a new frequency, which is known as millimeter wave. And millimeter wave means the wavelength, the waves which have wavelength in the order of millimeter. And there are different characteristics to this frequencies, that they have high penetration and diffraction losses, their blockages are significant, and their communication is highly directional. They will have smaller cell, higher density, and more opportunistic deployment, which you can see as it becomes looks more random. So as the cellular network has evolved over the years from 2G to 5G and beyond 5G, what main trends we have seen is, first is the densification of the network. Many days there are more and more towers being deployed, and some of them are deployed by the operator, and some of them are also deployed by the users. Like in the hostels, you will see these Wi-Fi routers, which are deployed by the hostel authorities just to boost up the signal. In malls, in downtowns, you will also see some towers which are deployed by their own owners of those properties. These are more opportunity deployment also. So you have one basic base station tower, and then you identify the coverage holes, and then you put some base station deployment there. And then because of this coexistence of different technologies, we get something called a heterogeneous network, which consists of many different types of base station, These differ in their power, transmission, number of antennas, and so on. Then we also see millimeter wave networks, which are more random and which have smaller coverage. And then we are also seeing Internet of Things, where you will see a high density of small power devices connected to each other. So once we have this, let's talk about how do we analyze or compute the performance of these networks. So let's start with the cellular network, and one of the basic cellular network model which is used, which is conventional, is known as the Wiener model. Right? Let's take a very simple one. In this, I have so there are different neighboring cells in a cellular network. So generally you can have different two-dimensional cells, but let's take a simple model. In one dimension, there are three cells model. So these three base stations are deployed, actually 2D. So, but we are taking a linear model. So there are three cells. And then there is a distance between this cell, three towers, equal distance, and then there is a user somewhere in between. Let's denote the location of the mobile at XY. And let's assume the intersite distance, which is the distance between this base station and this base station, is A. So if I take a mobile at XY, what is my serving power? Serving power would be given by fading multiplied by the distance to power alpha. Okay, let's assume I'm not taking shadowing or other factors into the place. Then interference, you have two interfering links. So the interference would be power from this and the power from this. So power from this base station would be h1 upon the distance from it to alpha, and the distance would be given if this is xy and the distance is a. The distance will be a minus x squared plus y squared. Similarly, from the other base station, the interfering power would be s2 upon distance for alpha. And our goal is, I can compute a signer from this, which would be a random variable. So I want to guarantee that depending on the location of x, y, what is the guarantee that the assigner was above threshold and with some probability. Right? Like for example, what is the value of A I should take so that the assigner coverage is more than 10 GB 90% of the time. So I have a assigner. If I somehow compare distribution of this, I can compute the probability and then I can set A. I can change A and then find out which A will give me the 90% probability. Okay, and that was a very simple case, but even if you look at this, you have 1, 2, 3 random variables, and if x and y are also random variables, suppose the mobile location is random, then you have 5 random variables, and solving this equation is really, really difficult. But that was a simple model. Actually, normally we have this 19-cell hexagonal model where this is the one cell and they have a nice collection of 18 cells around it. And if you want to compute the performance of this, you can guess how many random variables are there. So if you want to compute the performance, you cannot go for analytical approaches. The only thing people do is just take the simulation approach, simulate this network multiple times, generate all those random variables and compute the performance. Okay, but now there are different problems with the simulation. That is why we come with something called stochastic geometry. Okay, so let's see what is the need for the analytical frameworks. Why do we need to analyze these networks? So first is, in the past we had this nice 19-grid cell and the base station are deployed. But over the years, as the cell networks have evolved, there has been increasing randomness in the cellular-centric deployments. Right? For example, you see this deployment of this Wi-Fi nodes, they are more opportunistic and you're deployed. So you see more randomness in those networks. Even millimeter wave small cells, and you cannot predict exactly where the coverage would be, so you deploy opportunistically, and which looks like a random deployment. And then there's a problem with simulation approaches. So what are the problems? is that you can fix some parameters, compute the performance. You can take different set of parameters to compute performance, but you cannot guarantee that what will happen if I take any other parameter. Okay, or you can, if suppose you want to see the impact of density, you take different density and simulate the network, right? You get some discrete values, but still you cannot tell with 100% guarantee that the coverage should increase or decrease with the density. So if I have some tractable tool that provides some more insights and quick conclusions, I can look at the expression and find out, oh, okay, what is the dependency of density? So because of this randomness, the study which we have to do is the study of random geometry, because we have seen the signal power depends on the geometry. And if we want to analyze it, we need a tool which can analyze a random geometry based systems. And that is where the stochastic geometry comes in. It's not a new topic. It has been in the past. It has been used in chemistry and physics and other systems to model different real life phenomena. But in like 10 years back, this first paper, the stochastic geometry was introduced as a tractable approach to analyze various systems. And since then, it has been applied to many other tools. Okay. Now, there is one more reason to use this, because sometimes people say that if you look at the, first of all, in stochastic geometry, we model the base stations as randomly located. And then some people argue that if you look at the conventional deployments, they are more planned. So how does this random geometry-based model are valid for the realistic scenarios? So I have put three different figures. The middle one is the real 4G deployment from a US city. The left-hand side, you have a conventional planned hexagonal model where every tower is nicely located with the same fixed distance. And on the right-hand side, I have a Poisson random model where the base stations are randomly located. And you can guess that the real 4G deployment is somewhere in middle. It doesn't have all the cells exactly equal with the same intersite distance. And it is also not as random as the PPP deployment, because in Poisson deployment, you will see later on, some base station can be really close. There is no correlation in the locations. So when we can just expect that if we compute the performance of a 19 cell and a PPP model, both will be a little bit inaccurate, right? And real performance will be somewhere in between. And it has been found later on with a huge amount of validation that both models are as accurate as each other. Okay. None of them you can say that it is not good. So stochastic geometry based model give you same accuracy as the fixed models, but they give tractability also. Right. So there is one additional advantage that both have same accuracy, but the PPP gives us tractability. So you can look at the expression and find out what kind of relation different parameters have on each other. Okay, and that was conventional 3G and 4G models. But as we are moving ahead, we are seeing more and more small cell deployments, and they are even more random. Right, you can see two base station small cell tower which are really close to each other or even on top of each other. So stochastic geometry has become more and more relevant in these days for the modern networks. So what are we going to learn in this course? We will start with two basic concepts. One is point process. Okay, because I said the base station locations are random, so we need a model which can which can model a spatial pattern of points randomly located in the space. So a point process is nothing but a random set of random points in a d-dimensional space. And if you look at it's a random process, so different realization looks like a different set of points in the same space. We denote it by phi, which is nothing but a set of xi's. Right, so this is just a set, but it's a random set because these elements are random. And even the number of these points can be random also. Some relation may have 10 points, some relation may have 15 points, or even they can have an infinite network, so they can be infinite number of points also. Okay, this is xi denotes the location of point, I is the index set. Sometimes we can take finite numbers, sometimes we can countable number of elements. Okay, each relation we denote by small phi, which is a deterministic set of points. Okay, so the complete point process is a random process which denote the random location, but if I take point realization, it's just a deterministic points. Now, Poisson point take value phi with probability of some probability. So if I have finite number of or countable number of realizations, you can assign the probability to each realization. And then depending on different how the point process look like, you can have a uniform point process where the points are uniformly located. You can have clustered points where there are different clusters. And then you can have a non-homogeneous process where some location the density is more and some location density is less. What are the application of point process? How we are going to apply this? So when we talk about any kind of wireless network like cellular or AdHoc, we can use this point process to model the location of different nodes. Like in cellular setting, we can use it to model the location of base stations or uses, okay, which can be extended to model devices in AdHoc networks, different devices in head nets, okay, and we can also apply it to multiple internet systems, millimeter wave networks, and so on. Second thing is what we call Boolean models, which like in point process you have seen is a set of random points. Okay, and if at each point I assign some random shape, like for example, I put cycles of same size or different size on each of these points, or I put lines on in these points, then this set of lines is again a random process, which is a process containing random objects located at different locations. So this is known as the Boolean model. And how do model use these Boolean models? You can use them to model blockages. Like you have seen, there's a single user and there are different base stations. And these lines are like different building footprints. And if a building footprint fall in a link, then this link is blocked. Such kind of system can be modeled using the Boolean models. And you can also model SNR or SNR coverage cell. So each base station, these base stations are randomly deployed, and each base station has a region around it which defines its coverage or its cell. Okay. Connectivity also you can use Boolean models to show the connectivity, which you will see later on. Okay, so suppose this is a coverage area base station and this is another area base station. If they if some base station falls outside the coverage area, then it is not connected. And if it's fall inside, then it's a connected. Okay, so again, we can also say connected if there is a link between. So this base station falls outside this coverage, but there is a base station in between which falls on this coverage area. So this link is connected, and this also falls on this coverage area. So this link is connected. So via one hop link, these are connected. Right? So you can model this coverage areas using Boolean in the following way. Suppose these are network of sensors or base stations. Each has a coverage area. If they have same power, the coverage area will be same. If they have different power, they will have different. And you can look at this, you can model this using Boolean, and you can find out that this is not a connected graph. But if I increase the power, I will increase the coverage area, and then you can see this coverage area will be connected. So using multiple hops, you can identify whether a link is connected or not if you model a network using Boolean process.
Let us now come to the content of this course. In the first lectures, we have talked about introduction to modern communication network. We have seen modeling and analysis issue in modern communication system. Then we'll talk about, we'll give a short introduction to stochastic geometry. We will see why stochastic geometry is important. What are its application? And how do we validate these models? Then we will learn about the point processes, which is the core concept of stochastic geometry. And we will see how do we characterize them. Then we'll move to a specific type of point process, which is known as Poisson point process. We will define them, we will look at their types and properties. And we will talk about some operations on PPP, like thinning, displacement, and superposition. We will learn about Laplace functional and PGFL, which are two characterization of Poisson point process. And we will also talk about Campbell theorem. Then we will look at a specific type of point process, which are known as mark point process. These processes carry a mark with each point. So we'll look at its theory, how do we compute a distribution of mark. And then there's a theorem related to PPP, which is very useful in the analysis, which is known as Slavinac theorem. After learning these basic things, we will now move to one example. We will see how we can compute the performance of an ad hoc network. We will compute the characterization of interference. We will talk about transmission capacity and assign a distribution for this network. We will see some more examples of wireless networks, in particular downlink cellular network and uplink cellular system. We will compute interference characterization and assigner and rate coverage of this. We will also look at the impact of fading, shadowing, other wireless factors, and how we can extend these analysis to a MIMO system. Now we come back to the theoretical part. We will talk about something called a palm distribution, which is nothing but a conditional distribution, condition on a point at a particular location. We will see how we can compute this distribution and how it is related to mark point processes. An interesting theorem, Campbell-Mackay theorem, which is very useful in computation of various matrix, performance matrix, will be discussed here. We will revisit some of the prior concept from the perspective of palm distribution. Then we will move to one application of these palm distribution and whatever concept we have learned up to this point. Here we will analyze a heterogeneous network which consists of multiple types of base stations. We will look at its performance and how we can extend to a heterogeneous MIMO. We will also talk about when 2 point processes are equivalent, and we will use displacement theorem, which is taught in the PPP section. We will see how we can use equivalency PPPs to convert some problems, some networks to simpler networks where analysis is possible. Now we will move another concept of stochastic geometry other than point process. These are known as Boolean models, and it is used to model random geometry. So point processes are used to model some random pattern of point, while Boolean models are used to model the random pattern of objects, such as lines or circles. We will see how we can use Boolean models to model connectivity or coverage in a network. It's also used to model blockages in cellular networks. So one application for this will be millimeter wave networks, where blockage is a significant issue. We will see how we can use Boolean models to model blockages and then apply stochastic geometry tools to compute the performance of limited networks. We'll also look at some higher order characterization of point process, including moment measures, and they are used to characterize the distance, the inter point distance in a point process. We'll also look at some other important point processes, including cluster processes and repulsive processes. And we will see their application where these processes can be useful. The course will have a midsem and endsem, each of 20%. This is an online semester, so the assignment and quizzes together they hold 30 marks. And the course will have a project component, which is also of 30 marks. Note that some assignments may contain some programming or coding task. So students are expected to learn MATLAB by themselves. It's a very easy language, and I think this will also be useful in your for future research. So you should definitely learn this. Projects can be done in a group of two. However, expectation for the project delivery level will be according to the number of people in the group. So if there are more people, you need to work more. And student obtaining significant and publishable results in project component may get an A grade irrespective of their performance in other components of the course. So this is an incentive to do well in the project part. But decision whether the work is significant and publishable, that depends entirely on the instructor. So students are requested not to count on their projects only and also perform well in the course. And the project component will help in getting a good grade. And this is very important part. Use of unfair means is not allowed in any case. In case you are found cheating in any component, even if it's a small part of the course, you will be given an F grade. So I expect all students to adhere to some honor policy. Now let us look at the references for this course. You will have video lectures and they will be sufficient for this course. And here are some textbooks which you can refer to learn more. One is by Francois Beccelli and Bartek. It's Stochastic Geometry and Wireless Networks, Volume 1 and 2. It's available free online, so you can download this. There's one tutorial to Stochastic Geometry written by me. It's available on Archive, which is a good source to start learning on stochastic geometry. There is a textbook by Martin Henge on stochastic geometry for wireless networks. This is available in IITK library. And since stochastic geometry is an emerging field, some of the problems we will also see directly from the research papers.